Hi, I'm Professor Steve Miller. Welcome back to Introduction to Computational Fluid Dynamics, CFD. We have another special topic today on multiphase flow. Let's just look at some basic, very simple introduction to the idea of multiphase flow. What it is, the major equations of motion, that is, the modifications to the Navier-Stokes equations, and different applications. This is just an overview, and it should be known that many people have spent their career studying multiphase flow. It is, like the other special topics we're looking at, a very deep subject which one can be lost in. Let's look at our class overview. This class is mostly based on the wonderful book by Brennen, Fundamentals of Multiphase Flows by Cambridge University Press from 2005. If you get a chance to pick up this book, I highly recommend it. Now, in this class, we'll just have a quick introduction of what multiphase flows are. We'll look at the equations of motion, and we'll look at some examples from our everyday lives and some very interesting engineering situations. They invoke cavitation, which is like the bubbling of a high-speed or low-speed flow like in water or a liquid. We'll look at boiling and condensation, which we see every day in our kitchen when we're boiling water. And, of course, we look at particular sprays, and sprays are very important in industrial process, or maybe you've seen a spray from a spray paint can or something similar, or hose, a water hose into your garden. And finally, we'll look at something very interesting called kinematic waves. And we'll look at a number of videos at the end of the class, at least links to videos that I recommend to get a better idea what multiphase flow is. Note, we were looking at this in the context of CFD. This is not a comprehensive introduction or discussion of multiphase flow or physics or CFD. It's just a taste of the subject. Now, multiphase flow will be where any type of fluid flow will consist of more than one phase or component. Think back to your chemistry classes where you talked about phases of matter. Here we might have a liquid phase and a gas phase, or a gas phase and a plasma, or all three. All these are examples of multiphase flows, and I just gave examples on the previous slide of what these might be. Let's look at two other particular examples. For example, cavitating pumps and turbines for electrophotographic processes for paper making to the pellet form and of almost all types of raw plastics. All granular flows, that is like the flow of sand or coal or grain, are considered multiphase flows in some sense. They're granular flows. Or you might look at multiphase flows where there's a feature of environment, perhaps rain, snow, fog, avalanches. So if you're in environmental engineering or environmental effects or predicting weather, these are very important. Avalanches, mudslides, sediment transports, debris flows, and many others. So you can think in our everyday lives and engineering applications, multiphase flow is prevalent and everywhere and critical for our lives. In fact, many of the reacting flows, which is another special topic we touched on, is often seen as a subject of multiphase flow and computation. So let's look at our equations of motion and see how we might account for different phases. We still have the conservation of mass equation. And for a particular phase, we might write another conservation equation. We might say partial rho sub n of partial t of partial rho n uni partial xi equals script I n. Here, n is the property of the specific phase or component. For example, n would be g for gas, or n equals L for liquid. And so we can modify our equations of motion for particular phases and solve them. You're getting an idea now of what we're going to do to the next equations of conservation of mass and energy. Here, In will be the rate of the transfer of mass from one phase to another. You can imagine this must be conserved itself, and so we can write another conservation equation here. The sum of the transfer rates from one phase to another is balanced and equal to 0. Now, we call this particular equation the dispersed phase number continuity equation, which is shown in the first equation on slide 5 of this special topic. It is indeed a complementary equation of the conservation of mass, and they represent equations governing the conservation number of bubbles, drops, particles, etc. that represent a diverse or multiphase flow. Here, n sub d is the number of particles of the dispersed component per total unit volume. And so you might also look at the number of particles per unit volume if you're looking at purely Eulerian simulation. If the volume of the particles of component d, that is dth component, is denoted by v sub d, then alpha will define alpha d as goes to nd times vd. We can substitute this form back in the continuity equation, and we'll find a form that looks like this. This will show that the rate of transfer of the mass of the components of D into each particle is equal to the Lagrangian rate of increase of each mass of the particle. That's a simple relation between, of course, the traditional form and Lagrangian forms. We also need to modify the conservation of momentum of the Navier-Stokes equations. Now there's a little bit of differencing in forces in that there needs to be a conservation of mass still between the net forces in the kth direction acting on the nth component of the control volume. Now we can write a force on each particular n, and it must obey this particular law. Fnk t, that is, the forces, will go as the partial derivative with respect to time of rho n alpha n un k plus partial xi of rho n alpha n un k. This will complete, of course, the equations of motion for momentum, but we need to construct these particular forces. We need to include body forces that are acting in the control volume, the forces due to the pressure and viscous stresses on the exterior, and of course, the forces that each component imposes on the other components within the volume. Now, the first contribution will be the force due to the external force field. We can rewrite this way. The second contribution will be due to the tractions on the control volume between the particular phases of the fluid. This means we need to modify our stress tensor, partial sigma CKI or partial XI. And we can decompose that into a pressure and deviatoric stresses just like we did in our equations of motion formation for the original stress tensor. The third contribution of the forces is simply the force per unit volume imposed by Nk on other components of K. So we can rewrite a new force term to be balanced by the left-hand side on the individual phase momentum force equation. So now we can introduce what we call the individual phase momentum equation, IPME. If the momentum equations for each of the components are added together, the resulting combined phase momentum equation will become this one, which I've written on the bottom of slide 8. We can now write Newton's equation of motion for an individual particle for volume D if we care about Lagrangian approaches. Here we have the material derivative of course, the individual particle volume will be balanced by the forces which we've developed plus some gravitational force. Here again, we've defined the material derivative, but now we use U sub D. F will be the force that surrounds the continuous phase, which imparts on the particle direction K. We can expand this equation and use the definition of I sub D to obtain the diverse phase momentum equation. We now have to handle, of course, conservation of energy. In many multiphase flows, the different phases and or components are often not in equilibrium, and consequently thermodynamic equations and equilibriums might be appropriate for single flows which were developed in classical thermodynamics are no longer valid. We now need to examine the task of construction an energy equation for each of the components of the phases in multiphase flow. It will be necessary to define a total internal energy density for each of the components N of the multiphase flow. I'm going to rewrite it this way. This is a very typical component. Once again, we have an energy, kinetic energy, and potential term. So you can imagine there's an appropriate and obvious first law of thermodynamics that must be satisfied by the energy equation. By definition, here we've written out these particular terms and their expansions. Take a second to review it. Going through and filling in terms of the conservation of energy equation, we can write the combined phase energy equation, which we now have shown on the bottom of page 11. Take a second, read through the slide, and you can understand the terms of an equation based on the first law of thermodynamics, using the same nomenclature introduced, of course, for a momentum equation. We now have a multi-phase equation for conservation of mass, energy, and momentum, which we can go through and try and solve with a CFD solver. Let's look at some particular applications for multi-phase flows with these particular equations. The first is cavitation, and this occurs where a liquid system where it has pressures which fall sufficiently low to some value when the flow vaporizes, and vapor bubbles are formed within the flow. These are very important in perhaps submarine applications or marine applications where the flow behind a propeller cavitates. In fact, it's a quest for many hydrodynamicists and hydroacousticians to find flows which have no cavitation. Because, of course, cavitation destroys the material where these little cavitation bubbles burst, sending out tiny little shock waves, or they can create very loud flows, which might be detected by sonar. Now, it's very typical to create this nine-dimensional parameter or number to characterize how close the pressure is to the liquid flow to the vapor pressure for cavitation. This is the so-called cavitation number. It's the pressure minus the pressure vapor times the ambient temperature over a dynamic pressure of the density of the liquid with the mean velocity squared. So this is dynamic pressure, and this is a pressure difference. If we hit, of course, this particular value of 0, the critical value of cavitation, we would expect cavitation to form. Now, prior to the cavitation and its cause, the magnitude of the lowest pressure of a single phase will be given by the minimum value of the coefficient of pressure. If the cavitation were to occur when the minimum pressure reaches the vessel pressure, it will obviously follow that the value of the critical inception number, sigma sub I, would be simply given by the negative of the coefficient of pressure minimum. Now, cavitation in practice radically departs from C sub P minimum through many particular factors, which I've listed on this page. In the interest of time, I'll let you read through them. Let's look at some graphs of cavitation. On the x-axis, we have the radial coordinate, that is the radius of perhaps the bubble. And then we have the bubble pressure, P divided by P infinity. The pressure and radius are put on log scales. So this is from, of course, the experiments for the pressure distributions in a liquid before collapse and after collapse. The left is before collapse, and the right is after collapse. The bubble wall is drawn as a dashed line with particular labels, and you can see how the pressures change during formation and collapse of each particular cavitation bubble. This is basically a physical graph for you to understand the physical changes in pressures within the cavitation bubbles. We can also look at particular images of the cavitation bubbles coming near surfaces. On the right is perhaps an illustration which is most interesting. It's the collapse of a cavitation bubble close to a solid boundary in a quiescent liquid. These are theoretically derived shapes. Let's look at these theoretically derived shapes with those of experiment on the left. On the left, we see a series of photographs which show the development of a microjet in terms of a bubble collapsing very close to its solid wall. On the left, the wall is on the top of the page, and on the right, the theoretical predictions, the wall is on the bottom. So you'll have to sort of flip around the right figure to see. And you can see these types of cardioid shapes forming inside the particular little bubbles as it progresses near the wall. So you can see from 0 to 7, and compare that from, say, 8 to 17. So this is theoretically predicted and seen in experiments and can also be predicted with CFD. We care a lot about cavitation bubbles and how they form near walls because, of course, they create damage. Here I've shown some particular photographs of damage due to cavitation. The top is major cavitation damage to the blades discharged from a Francis turbine. So here's the turbine blades, and these blades have been eroded due to effects of cavitation. You can see by eliminating cavitation through CFD studies might greatly prolong the lifespan of these types of liquid turbine systems. The lower photograph is the localized cavitation damage on a particular blade from a mixed flow prompt impeller, and the propeller blades themselves, of course, are made of aluminum. So you can go in and see these microscopic or even large-scale effects over time from cavitation. You can imagine how ineffective these blades are while they're still running with effects of cavitation. And of course, these will eventually fail and fall apart, which would be catastrophic in an industrial application and might even lead to the loss of life or detectability of a submarine or hydrodynamic system in a warfare situation. Cavity noise is a very, very interesting subject, and reducing cavity flow in a submarine application are closely guarded national secrets of any country using submarines. Let's look at the acoustic spectra from cavitating flow and non-cavitating flow. On the left, we have a y-axis of the noise energy spectra. The x-axis is frequency. The graph is, of course, of acoustic power from a particular valve under operating a non-cavitating flow. Sigma here is the non-dimensional cavitation number. And this part of the spectra is where there's no cavitation given by the value. Now you can see higher values are noisier. For example, at 10 to the fourth, 10,000 hertz, we have a value of, say, 10 to the third power spectral density. If the flow starts to cavitate, we have tremendous increases of energy at all these frequencies at, say, 10,000 hertz and higher. And so this might be undetectable, but at higher noise levels, it creates very large noises, which could, of course, reduce vibrations, which could lead to failure and structural weakening of the members of the device. On the right, they show the same type of signals from, say, a single collapsing bubble. So say we have a cavitation bubble and it collapses. It'll create a pressure time history that is the wave. This is measured in kilopascals. So on the x-axis, we have the time in microseconds, and you can see we have something that looks very much like a shock waves, or very, very large spike in acoustic pressures in the order of kilopascals. That kilopascal of 5 kilopascal is a very, very, very loud sound. And of course, that could lead to destruction of a device. Let's look at other multi-phase type flows. And this one is probably more familiar to anybody who's boiled water in a kitchen or has looked at industrial boiler applications in chemical engineering. A presence of a solid surface might help the rapid supply or removal of latent heat and energy, and also induce a phase change. So if you go in your kitchen and boil water, you can look down and see these tiny little vapor bubbles forming. It's the same process. You're having some boiling condensation on your stovetop. How cool is that? And it's a fun kitchen experiment. You'll see that the solid surface could be a plane, which is vertical or horizontal and containing a surface, or maybe interior external to a circular pipe. Now, in a very most common configuration, known as pool boiling, is when a pool of liquid is heated from below through a horizontal surface. This is your stovetop kitchen example. We have sketched your heat transfer rate and delta temperatures in your lower left of the figure. Now, when the pool as a whole has been heated to a temperature close to the temperature TE, the onset of nucleation and boiling will occur, and bubbles form at the so-called nucleation sites on the wall and grow to a size at which its buoyancy forces will overcome surface tension forces, acting at the line of the attachment of the bubble to the wall. The bubbles will then break away and rise through the liquid. This is observed through this nucleation process through the lower right. Here, we have a heated surface, which might be, of course, your pan, and the water exists inside the pan. This little condensation vapor formation will form at the nucleation site, at the site in the layer of the superheated fluid. So this is a formation of a multi-phase flow with a heat. Now, condensation is a little different. This is where we might have a rod that is very, very cold in a hot air on a humid day. You can then see the condensation on the particular rod. You might also look at a particular very, very cold drink on a very, very warm and humid day. You'll see that, of course, little bubbles are forming on the side of the glass. This is a little bit annoying for some people, and of course can increase the rate of heating of your drink. And so you wouldn't want condensation to form on your particular glass. This is just the opposite process in a sense of boiling, that the condensation, the vapor in the air becomes liquid and forms a liquid film which falls down on the side of the glass. This is another classic multi-phase problem in our everyday lives. Sprays are important also, especially in industrial processes. They might be used in, say, inkjet printers, dynamics of spillways and plunge pools, or simply a garden hose. Or perhaps you have a spray bottle to water plants or something, or orchids. Now, they're formed when there's an interface between a liquid and a gas, and it becomes deformed and droplets form and break away from the major part of the liquid element. Let's look at some dynamics of sprays in the ocean. So next time you go to the beach or ocean, you can look for the sprays, and instead of thinking about your pina coladas and beach umbrellas and balls, and you can look at the waves and you can look at the sprays of the ocean as you go along the seashore. So here in this case, we might have a little droplet of water hitting a free surface. It'll create a film, and that film will break up, which causes a jet, and the jet will break up and create this type of misting. You can see this in pictures in the bottom. This is like one of many examples of how these ocean sprays, or atomization, if you will, do these little water droplets moving around the ocean to create the ocean sprays. You might also look at water jets, which is the classic hose problem. For example, here's your garden hose spray taken from the side. You can zoom in at the surface between the water and air, and you can see how these little droplets form in the air and come off, and they'll break apart and become its own little spray. This happens at different of course, speeds, and is all due to different types of instabilities in the flow. So to really understand this problem, you have to understand the instability theory and its combination between a multiphase flow of water and a gas. We can also look at these multiphase flows as a combustion process, and for sprays and combustion is a very important field. For example, in an internal combustion engine, you'll have a fuel injector, which of course is spraying an atomized fuel into the combustion chamber, which has oxygen, and it's compressed, and a combustion chamber occurs. You can see this process in these particular plots in this figure. Spray combustion is seen in these particular figures too. I'll let you take a few minutes to look through them. Now, there's many videos to understand just the general physics of multiphase flows and combustion available online. I've posted just a few from multiple sites that are posted on YouTube or on their original sites. Look at cavitation of propellers. It's interesting to look at the cavitation and basically nucleation and vapor formation in a liquid flow. You can also see these multiphase flows that say air-water multiphase flows like hoses, etc., and many examples. NASA has shown videos of flow boiling and condensation experiments, fundamental experiments. Argonne National Labs has shown multiphase simulations of nuclear reactor flows with CFD. There's the so-called Taylor bubble multiphase flow, which is a fundamental experiment. And there's a really fun video called Inner World of Collapsing Bubbles. This is just the tip of the iceberg of this entire field of multiphase flow and CFD, which is so interesting and fascinating. You can spend a lot of time looking at it, and it's a lot of fun. Today, we have just touched the basis of multiphase flow and quickly outlined the formation of the equations. To understand them in depth, I recommend getting the books which I referenced in this class and looking at some of the videos and material online. Better yet, you can take a graduate course in multiphase flow, and there's many experts in different universities in different types of multiphase flow. You can even find one in particular that you're especially interested in or a particular application and pursue that. We've discussed these different types of physics today, including the basics of cavitation, boiling, and condensation, and showed just verbally real-world examples where these might occur. So the next time you go to the beach or into your kitchen, look for these multiphase effects. The next time you're on a ship or on an airplane, think about the multiphase effects on the ocean surface inside the propulsion systems of these vehicles. We also basically looked at sprays. Now, it happens to be true that University of Florida is one of the centers of multiphase research in the world, and we have many people who are experts in this field. So you're very lucky to be here, and you can pursue research activities with one of those professors. Thank you very much for your time today. I'm Professor Steve Miller.